Here are the integration techniques we have so far. So before you entered on campus this semester, you already had substitution under your belt. We did take a peek at integration by parts, then trigonometric intervals, then trigonometric substitutions. What's next on our list is partial fraction decomposition, rationalizing substitutions, and what I refer to as our Weierstrass substitutions. Let me come back right here. Partial fraction decomposition, or PFD. So I must confess, I could actually evaluate this integral by completing the square on x and committing to a hyperbolic substitution. I won't go there. I'll show you a different technique. This, in the integrand's position, is a rational function. In addition, it's a proper rational function. I should say expression instead of function. We'll make a distinction. It's rational because the ratio of two polynomials. It's proper because the degree upstairs is strictly less than the degree of the polynomial downstairs. So here I go. I will pull out my nifty little piece of scratch paper. I will take my fraction, factor its denominator, and I will decompose it into the sum of two other fractions whose denominators are easier to deal with. Because this is proper, these two must be proper. But they're, please excuse me, but their denominators are of degree 1. So the numerators can be as great as degree 0. That means they're merely constants. Now, before we get started, can you appreciate why this is going to work so well? If I can rewrite this fractional expression in terms of the sum of these two, then we could just state the answer. These two are just natural logs when I anti-differentiate. So let's dive in. I'll get rid of fractions. I could equate coefficients of x and constants on both sides of the equation, create two equations and two unknowns that are linear, and solve that system of linear equations. I'm tired, I tend to be lazy, so if you don't mind, I will use a shortcut instead of going through all that work. I will allow x to be the 0 of one of these linear factors. What I do, this entire second term on the right-hand side completely drops out, and I'm left with this equation. That means I know what a is. Likewise, allowing x to be the 0 of the other linear factor. When I substitute that value in for x, this first term on the right-hand side completely drops out. I now have b. Now that's really nice to have, because this means this integral can now be re-expressed in the following fashion. I now anti-differentiated. And I will simplify.